Most real-world electrical systems do not operate with constant voltages or currents. Instead, they use signals that continuously vary with time, especially sinusoidal waveforms. In this lesson, we will learn AC circuit analysis and how circuits behave when driven by alternating signals. AC circuit analysis is the study of electrical circuits driven by alternating current or voltage sources that vary periodically with time. Unlike DC circuits where values remain constant, AC circuits involve continuously changing signals, typically sinusoidal in nature, which require different analytical methods to understand their behavior. In AC analysis, voltage and current are no longer treated as constant values, but as time-dependent waveforms. This introduces additional complexity because circuit elements respond differently depending on frequency. Resistors, capacitors, and inductors each behave in unique ways when exposed to alternating signals, making frequency an essential factor in analysis. AC circuit theory is fundamental because almost all communication systems, power distribution networks, and electronic devices operate using alternating signals. Understanding how circuits respond to AC input is essential for analyzing signal transmission, filtering, and energy transfer in real systems. The most common type of AC signal is the sinusoidal waveform, which varies smoothly over time and is characterized by amplitude, frequency, and phase. These parameters determine how the signal behaves and how it interacts with circuit components. When a sinusoidal voltage is applied to a circuit, the resulting current may also be sinusoidal but can differ in amplitude and phase depending on the circuit elements. This phase difference becomes especially important when analyzing capacitors and inductors, which introduce time delays between voltage and current. Because of this predictable structure, sinusoidal signals form the foundation of AC analysis. They allow engineers to represent complex time-varying behavior in a mathematically manageable form. One of the most important aspects of AC circuit analysis is frequency dependence. Unlike DC circuits, where frequency is zero, AC circuits respond differently depending on how fast the signal changes over time. Capacitors and inductors are particularly sensitive to frequency. Capacitors tend to allow high-frequency signals to pass more easily, while inductors tend to oppose high-frequency signals. This frequency-dependent behavior is the basis for filtering and signal shaping in electronic systems. As frequency changes, the impedance of circuit components changes, which directly affects how voltage and current are distributed in the circuit. Understanding this relationship is essential for predicting circuit behavior under different operating conditions. In engineering practice, AC circuit analysis is used to design and evaluate almost all electronic and electrical systems. Power systems rely on AC analysis to manage energy transmission over long distances, while electronic circuits use it to process and manipulate signals. Filters, amplifiers, and oscillators are all designed using AC principles. Engineers analyze how signals change in amplitude and phase as they pass through different circuit stages, ensuring correct system performance. AC analysis also provides the foundation for more advanced techniques such as frequency response analysis and system modeling, which are critical in modern electronics and RF design. In RF engineering, AC circuit analysis becomes the primary tool for understanding system behavior because RF signals are inherently high-frequency alternating signals. Every RF system operates in the frequency domain, where voltage and current continuously vary over time. Impedance matching, signal reflection, and transmission efficiency all depend on AC behavior. Engineers must carefully analyze how signals propagate through components and transmission lines to ensure minimal loss and distortion. Understanding AC circuit analysis is essential for RF engineering because it provides the mathematical and conceptual foundation for communication systems, wireless networks, and high-frequency circuit design. In this lesson, we learned that AC circuit analysis focuses on circuits driven by time-varying signals and how components respond differently depending on frequency. This forms the foundation for understanding signal behavior in power systems, electronics, and RF engineering. In the next lesson, we will explore phasor representation, and learn how AC signals can be simplified into frequency domain vectors. If you found this useful, like the video, subscribe, and follow for the next lesson.